That's the problem.
For the previous problem, that was what we found in XOC.
So there, wow.
Is the one over, am I seeing the right formula?
Yeah, what I had looked at before was right. But, oh well. So therefore this is off. That is off. Let's bring this back to 30 microfarads like it was. So this would be omega C squared. Sorry about that. Sorry, it's when I get too arrogant. Wonderful things. All right, so now, given that,
10.152.
so we end up with 1 over the square root of something still.
No, that's what I got for the entire thing.
Oh, for the entire, for the
entire
impedance.
The impedance is 10.152.
Units? What are the units of impedance?
Ohms. Oh, and that's what I was doing the first go around as well.
Oh, the number that you gave us was for the whole thing?
Was for the whole thing, yeah.
Wait, you jumped ahead.
XOC.
He was leading our phaser. Sorry, Ethan, you were saying?
XOC equals 106.1033.
Okay. 106.103.
Yeah.
Ohms.
What are the units of Z, no, Z?
What are the units of C?
The Z.
The Z?
Yeah.
Ohms.
Ohms. So they're all ohms.
Yeah. All right. Questions on this?
Is this gonna be like the bulk of the chapter? It's understanding what's going on right here.
The chapter includes Faraday's law and this.
Oh,
So,
well, we already did Faraday's law, right?
yeah. Yeah, so chapter 23 is, this is chapter 23, is electromagnetic induction. So the induced EMF is part of this chapter. And then inductance and AC circuits.
This is the AC circuits.
Yes.
I got for the impedance 52.23.
For the final answer?
Yeah.
Oh, so I'm immediately wrong.
Sorry, so it's gonna be one of those. Let's see, so 106 squared. Work your own calculator.
Right.
You're wrong once, though. You're wrong every time. Is that the way it works?
I got the first answer if you don't square the XC value, 1 over XC squared.
Ah.
Oh, I may not have done that one. Hold on.
Let me see.
So I was right, just automatically cross yours out.
It's okay. Fair.
Like a stop
Yeah,
clock.
that's what I did.
All right.
Maybe scared. Yeah, I got the 52.
Sheet.
Questions?
Problem 24.
You guessed. All right. We have talked about inductors here, I believe, as well as we derived the formula for them. One of the groups I did not, one of the groups I did, so I'm pretty sure I did not for the other group yet.
I think you did.
Oh, yes,
Okay.
the L, the negative L, delta I over delta T.
But I did I derive Eli of why the voltage leads? Or just presented?
Right, yeah, with the, is this what we're talking about?
That's a capacitor. That's when I mentioned Eli. Is that,
No, that would be.
there we go.
Yep.
Okay, I did derive it. All right. So, I get an AC power supply, and I put a resistor, a capacitor, and an inductor into a series circuit. So we now have 4 components, each one with a voltage phasor and a current phasor, so there's going to be 8 phasors. So what is going to be common to all of them?
Voltage.
Current. They're in series, it is indeed current. Now, I think the textbook puts when you're doing this, puts it straight horizontally, but that just, aesthetically, that disturbs me. So, so this is epsilon sub naught, which is equal to V sub R, which is, that is the current from the power supply, which is equal to the current across the resistor, which is the current on and off the capacitor, which is equal to the current for the inductor. And I need to make sure my C's and L's look distinct.
Awesome sauce for out of the way.
Yep. Think half the problem done like that. It's that simple. Now we bring in, let's do the voltage across the resistor. Like, which way? Second, was that the second quadrant?
Opposite of the current thing?
90 degrees.
90 degrees.
Or the resistor?
Yes. No.
Or is it the same for the resistor as well?
Is it?
Yeah, I think the resistor is the one that's just the one where we just draw it shorter than the other one.
Yes.
The resistor's in phase.
In general, if we have a problem like this, most like these two things will be in phase and very similar every single problem.
For the resistor, the current and the voltage are always in phase.
So,
They would only get tricky if I threw another resistor into the problem.
if you have 2 resistors, are they
Then-
both in phase or is one out of phase probably?
The current across the individual resistors in phase with the voltage for that resistor.
Okay.
But whether they're in phase or not depends upon how I set up the circuit.
Will we have to do a problem with multiple resistors?
I have not yet, but you know, if I believe in you, if I have faith, if I think that you're capable of doing it.
Okay. So the
So,
voltage.
you're in favor of me doing it?
Sure.
Yeah, there we go.
Stop giving him ideas.
All right, so, we have 3 more current phasors to do, and power supply will be the last one.
Wait, that was, that's supposed to be V, not I.
You are correct. Because I seem to be prone to careless errors today. Thank you very much.
So then the V across the capacitor is the one that is 90 degrees to the, I guess, left, second quadrant.
No, it's gonna be in the 4th quadrant. Because the current's supposed to lead.
Ice.
Yeah.
Current leads.
Mm-hmm.
These things are spinning around like that,
Yeah.
so. For the capacitor.
Why would it not just be 90 degrees in the second quadrant? Because that's still ahead of it, I guess.
Yeah, you want it so that the 90 degrees that, given the memory trick of I before E, that the current comes before this as they spin around. That apparently is not doing much for you.
No. My question is, like, the last one, we just had this one, and then we went 90 degrees to the left, and that one was still ahead of that
Then
one.
what we just did, I think I erased it. It wasn't on this one, right?
No.
It was not. So the one that we just did, it was the current that was leading. We
Yeah.
started out with the voltage,
Yeah, we-
and then we drew the current 90 degrees ahead. So I have my two phasors that are 90 degrees apart,
Mhm.
and they're spinning around like this.
Yeah.
For a capacitor, this one is current, this one is voltage.
Okay.
And so the one we just did was like that, this one is like that.
Okay.
Ugh, I'm stretching for work today.
Okay, so we can kinda,
So suddenly I had a flash of $1 million idea. There's Mickey Mouse watches. How about a Mickey Mouse phasor diagram where the hands are? $1 million idea. Okay,
the voltage for the power supply, or the
Not
ESOP
yet.
not?
not yet, because we still have the inductor. Because I know the voltage for the power supply has got to be the sum of these three voltages here.
The voltage for the inductor is gonna be ahead of the current. But ahead by 90?
Yes.
Or- Okay.
Yes. So voltage, and I'm gonna redraw that one so it looks more like a 90-degree angle.
When something in terms of phasors is ahead of another thing, is it always 90 degrees? For our case.
If you're talking about the individual component of capacitor or inductor, yes, it's always 90 degrees. So that's V sub L. Now, I know that for the power supply, it's the sum of these three phasors. But I have two of them that are diametrically opposed to each other. Anti-parallel in a sense. So how do I resolve that? How do I add these three? Well,
Is it just equal to VR?
pardon?
Is it just equal to the?
No.
No.
Even though I might have drawn VL and VC to be the same length, let's not assume that. Now, without more information, it's difficult to know which one's going to be longer, so let's just assume one of them is longer. So I'm just going to represent that by actually just drawing a longer one. I don't know if that one's longer or not. It does not matter in terms of finding the impedance.
Question, if they were the same length, if the problem stated in the math worked, would it just be VR?
Yes, it would, in that case. So if I have two vectors in opposite directions, how do you add them?
Or we put them on top of each other?
That's not how you do it.
And then the difference in the length?
Okay. So if I had a vector that's 3 newtons to the, that way, and a vector that's 2 newtons this way.
It's one Newton to the right.
Yeah. So the same thing's going on here, is I've got this going this way, this going this way, and the difference is going to be a vector going whatever the difference in the lengths is. So this blue line right here is VC minus VL. So now I'm gonna add that, since I just added those two, I'm gonna add that to VR, and I get my right triangle again. And we could go for some stunning visual. Purple's on the ground. I'll probably put it there, all right. So there's epsilon, so not. So epsilon sub naught squared is equal to VR squared plus VC minus VL squared. This is equal to the current coming out of the power supply times Z. And this is the current across the resistor times the resistance plus the current across the capacitor, squared. Current across the capacitor times the voltage across the capacitor. Current across the capacitor times the capacitive reactance minus current across the inductor times the inductive reactance squared. I know my currents are all the same. I can factor I out of this and we get an I squared. So just divide everything by I squared. And so I get my impedance squared is equal to my resistance squared plus the difference between my capacitive reactance minus the inductive reactance squared. So my impedance is the square root of R squared plus 1 over omega C squared minus omega L. Minus 1 over omega C minus omega L. The difference squared.
And what is, and L is the,
Inductance.
Why is different? Or why is omega L not over 1?
It comes down to that the voltage of capacitance depends upon the charge. And the voltage of an inductor depends upon the change in the current. So it's like having so I know that I is the change in Q over the change in time. And so the voltage of a capacitor depends upon this, actually depends upon this. And so the current is related to basically the slope of that, of the charge time graph. Whereas the voltage across the inductance is proportional to the change in the current over the change in time, which is the slope of the charge time graph.
Oh,
I mean, that's ultimately where the difference comes from.
makes some sense.
In a slightly different point of view, this could be a calculus reference. That I have charge here. The voltage of the capacitor depends upon the integral, and the voltage of the inductor depends upon a derivative.
Good. I haven't got to either of those, so.
Yeah.
So,
Integrals you'll get second semester.
well, now they started the last chapter of Calc 1. So like the last 2 weeks is integrals,
Okay.
and they do. So it's easier in Calc 2.
if we were taking 252, is Calc 1 enough to know what you're doing with the integral?
Calc 1, you need to be in Calc 2 or have done Calc 2 to take Physics 252.
What about 251? Same then?
I mean, if you're in 251, could you?
If I'm in 251, do I need to be taking or have taken Calc 2?
You need to be, I think I messed up my numbers there. If you're in 251, you have to be in Calc 2 or beyond,
Okay.
or past it. It's a assume that you already know how to do derivatives when you get into the University Physics 1 or General Physics 1.
That's what I'll do. Joys to me, fall semester.
Tears of joy.
Here's a joy.
All right, other questions? All right, so naturally, we just did an RLC series circuit, so let's do an RLC parallel circuit.
Are we not gonna plug in Chuck this year?
Nah.
Oh, right at the very end, you did not plug in Chuck.
So what's the first thing you do?
Draw the voltage.
Why?
They're all equal.
Okay. The voltage across the resistor is the voltage for the capacitor, which is the voltage for the inductor, which is the amplitude of the voltage for the power supply. All right. Now what?
The voltage, the current for the resistor is in phase.
Okay.
The current for the inductor will be 4th quadrant and 90 degrees.
And then the capacitor will be beyond.
And then taking the difference.
I guess I do L bigger this time.